Introduction. What's Pascal's wager? Pascal's wager is one of the most well-known and established arguments for religion, and you can hear it being used to this day. Proposed by the French mathematician Blaise Pascal in the 17th century, it's an argument based on probabilities. A modern version of the argument can be summarized as follows. Let P of God be the probability that God exists, and let P of not God be the probability that God doesn't exist. Moreover, let R of God be the reward given by being a follower of God, and let L of not God be the loss of being a devoted follower if God doesn't exist. Then we get that the expected, or averaged reward for being a theist is given by the formula P of God times R of God minus P of not God times L of not God. Since it's possible that God exists, P of God is not zero, and since God bestows infinite grace unto his followers, R of God is infinite. Therefore, we get that the product P of God times R of God is infinite, and while the product P of not God times L of not God is at most finite, this implies that the expected reward for being a theist is infinite. In other words, you should believe in God. Although many people find this argument convincing, it has received massive amounts of criticism over the years. But nobody seems to question the mathematical sanity of the calculation of infinite expected reward, and that's what I'd like to do in this video. Why do we accept that the product of an infinite number with a non-zero number must be infinite? While this question might seem odd at first glance, it actually reveals how complicated something as seemingly simple as a real number actually is, and it gives rise to some interesting ideas that far too few people are even aware of. Part 2. What's a real number? Pascal's formula for expected reward works well if we are only dealing with finite real numbers, but what happens when we try to use the same formula for infinite real numbers? And what do we even mean by that? What's an infinite real number? If we wish to have a hope of answering this question, we need to understand what a real number is. In short, the set of real numbers, denoted by R, is the set of numbers needed to identify every point on a straight line of infinite length with a unique number. Let's see how this is normally done, starting with the integers. Beginning by marking out an origin point, represented by 0, and a point to its right, represented by 1. We call the distance between these the unit length, or whole step. We then use the integers, that is the whole numbers, to identify every point on the line which can be reached from 0 by walking a finite number of whole steps in either direction. Next, we introduce the set of rational numbers, which is a set of all numbers that can be written as a fraction of two integers, with the denominator being non-zero. To see which points on the real line are represented by rational numbers, we do the following for every possible denominator n. First, we let an nth step be 1/nth of a whole step, with steps in the right direction being positive. Then, we identify the point located k nth steps away from 0 with the number k over n for every possible integer k. As n grows larger, more and more of the points in the gaps between integers are identified with rational numbers. But even if we continue the process of filling the gaps between integers by rational numbers, this is not enough to cover every single point on the real line. For instance, no matter which denominator n we choose, we can never represent numbers such as e, pi, or the square root of 2 as an integer divided by n. But this raises an important question. How do we actually construct numbers such as e, or pi, or the square root of 2? How can we pinpoint them on the real line if they cannot be expressed as rational numbers? Part 3. Real numbers as sequences. To put it bluntly, we define real numbers in the following way. A real number x is the set of all rational sequences that converge to the point x on the real line. That a sequence is rational simply means that it's a sequence only consisting of rational numbers, and we say that the sequence converges to a point x if the numbers an in the sequence get closer and closer to x as n increases. Although the numbers an in the sequence could be far away from x for a couple of indices n, the general trend should be that an gets arbitrarily close to x as long as the index n is large enough. As an example, the number 1 is a set containing both the constant sequence of only ones and the non-constant sequence, beginning with 0.9, followed by 0.99, followed by 0.999, and so on and so forth, since both of these sequences converge to 1. But this convergence can also be somewhat chaotic in the beginning. The real number 1 also contains the sequence 0, followed by 502, followed by 65 over 79, followed by -11, followed by 1, followed by 1, followed by 1, and so on, since the only thing that matters is what the sequence converges to, not how it varies in the beginning of the sequence. Although this definition might seem a bit strange at first glance, it's actually a rather natural way to define the real numbers. After all, we want each point on the real line to be represented by a real number x, and any rational sequence that converges to that point contains information about where the point is located. So why not just store these sequences within a number x, which then contains all the information we need to reach the desired point? The only real question is how to treat these collections of sequences as actual numbers. That is, we need a way to add, subtract, multiply, and divide these objects in a way that agrees with these operations for rational numbers. As it turns out, we can define these operations entry-wise in the following way. Suppose we have two real numbers x and y. If we want to calculate the sum x plus y, we begin by choosing a representative sequence ax for x and by for y. Then we calculate the sum entry-wise, that is, a of x plus b of y equals a1 plus b1, followed by a2 plus b2, followed by a3 plus b3, and so on, which then represents the real number x plus y. In a similar manner, we can calculate x minus y, x times y, and x divided by y, provided that y is not 0 in the last case. The only thing one needs to check is that no matter which representatives a, x, and b, y that are chosen, the sequence representing x plus y, for instance, approaches the same point on the real line no matter what. This turns out to be the case, and an intuitive way to realize this is to note that no matter which sequence we choose to represent a number x, the entries of the sequence will only differ very slightly from x for a large enough index. And thus every sequence contained in x can be thought of as essentially the same for large enough indices. There is, however, one big problem for us with the real numbers as defined above. Since every number only contains sequences that converge to a specific point on the real line, there is no infinite number in this set. And that was the whole point. We need an infinite number to deal with Pascal's wager. So what do we do now? Part 4. Beyond the real numbers. Before trying to extend the system of real numbers to a number system including infinitely large numbers, let's try to describe why the set of real numbers is a good way to extend the rational numbers. First off, the set of real numbers can be defined using only sequences of rational numbers, and the rational numbers can be described in the real number system as the set of numbers that can be represented by a constant sequence of rational numbers. Secondly, as with the rational number, it's possible to order the real numbers, that is, given two real numbers x and y, then either x equals y or one of them is larger than the other. Moreover, this ordering is compatible with the notion that the larger number is placed to the right of the smaller number, just as it is with the rational numbers. As with rational numbers, we can do basic arithmetics with real numbers. That is, we can add, subtract, and multiply any two real numbers, and we can divide any real number by any non-zero real number. Another way of phrasing this is to say that R is a field. And finally, these basic arithmetic operations, addition, subtraction, multiplication, and division for real numbers, are compatible with their counterparts for rational numbers. That is, if we take two rational numbers and add, subtract, multiply, or divide them, it doesn't really matter whether we view them as rational numbers or if we view them as real numbers. The end result is the same number in either case. With this in mind, we We go on to consider sequences of real numbers to see if there is a good way to extend the system of real numbers to include numbers that can be viewed as infinitely large in some sense. Since convergence is what prevented us from having infinite real numbers, we will now consider arbitrary sequences. Like before, we define addition, subtraction, and multiplication of sequences entry-wise, as this ensures that our arithmetic operations are compatible with their real counterparts. However, before we can tell which sequences should be identified with the number 0, it's going to be difficult to define division. Let's consider two different sequences that earlier would have been considered as representing the same number. First, we have the constant 0 sequence, and secondly, we have the sequence epsilon, which is 1 followed by 1/2, followed by 1/3, and so on, which converges to 0. We note a few things. First off, the 0 sequence behaves like we would expect from the number 0 in the sense that for any real sequence S plus the 0 sequence is once again S, and S times the 0 sequence is the 0 sequence. And secondly, the epsilon sequence does not behave quite like 0. For instance, if we let n be the sequence starting with 1, followed by 2, followed by 3, and so on, we see that epsilon times n is just the constant sequence of ones. From this we see that although the epsilon sequence converges to 0, it should not be used to represent the same number that the 0 sequence represents in our new number system. This observation might lead one to believe that two sequences that are not identical should not be able to represent the same number. That is, in this number system, there is a one-to-one correspondence between what we call a number and what we call a sequence. However, this would lead to some strange outcomes that don't make a lot of sense if we want our number system to extend the real numbers in a similar way to how the real numbers extended the rational numbers. As an example, consider the following two sequences. First we have A, which is the sequence starting with 1, followed by 0, followed by 1, followed by 0, and so on. And then we have the sequence B, which is the sequence starting with 0, followed by 1, followed by 0, followed by 1, and so on and so forth. If we were to decide that distinct sequences should be seen as distinct numbers, then the product A times B is just the 0 sequence. But neither A nor B would then be considered 0. And this has a direct consequence that we would not be able to define division in our number system in a sensible way. So at least one of the sequences A and B should be considered as representing the number 0 in our new number system. At the same time, both A and B cannot represent the number 0, since the sum A plus B is equal to the 1 sequence, which should not be used to represent 0. In other words, one of the sequences A and B must represent the number 1, and the other must represent the number 0 in our new number system. But how do we tell which sequence should represent which number? There is an infinite amount of examples similar to the one we just went over with the sequences A and B, and the same problem arises for each of them. How do we tell which of the sequences should represent 0 and which of them should represent 1? Is it even possible to find a logically consistent way to do this? In other words, can we find a logically consistent and rigorous way to construct a new number system, which we may call star R, out of sequences of real numbers, such that 1. Star R is a field, that is, we can do all basic arithmetic operations without issues. 2. Every real number can be represented as a constant sequence in star R, and the arithmetics in star R are compatible with the arithmetics in R. And finally, it's possible to compare which of two numbers in star R is larger than the other, and such that star R contains infinite numbers. Amazingly enough, this can be done, and the resulting number system star R that we get is the set known as the hyperreal numbers. Intuitively speaking, one can say that in the system of hyperreal numbers, two sequences represent the same hyperreal number if they agree on a large number of indices. For instance, if the two sequences only differ at a finite number of indices, they are considered equivalent and thus representing the same number. A more precise way of phrasing that two sequences represent the same hyperreal number is to say that the set where these sequences agree is included in a non-principal ultrafilter. And for those who are interested in seeing a more rigorous definition of what I've talked about in this video, I will include a link to an excellent series of lectures outlining the construction of the hyperreal numbers in more detail. The only thing left for us is to have enough courage to embrace this new number system, and we'll finally be able to treat Pascal's wager with the mathematical rigor it requires. So, what is an example of an infinite number in the world of hyperreals? Well, we've already encountered one brief example previously in this video. Remember when I talked about the sequence n, which is 1 followed by 2 followed by 3 and so on? This sequence represents a hyperreal number, often denoted by capital N, which is strictly larger than any regular real number, as the terms in the sequence steadily grow larger the farther along the sequence we get. In other words, the number represented by this sequence is infinite. And so we have finally managed with our goal of creating a number system containing infinite numbers. But there is a flip side to this. If we have infinitely large numbers, we will also have infinitely small numbers to balance them out. For instance, since the number n exists among the hyperreals, and since division is possible, the number 1 over n also exists, which is a non-zero number that is infinitely small. In fact, we've already encountered this exact number before as well, when we considered the sequence epsilon, which is 1, followed by 1/2, followed by 1/3, and so on. Since n times epsilon equals 1, we see that the epsilon sequence represents the hyperreal number 1 over n. In general, hyperreal numbers that are infinitely small are called infinitesimals. And for the Leibniz enthusiasts out there, yes, these are exactly the kind of numbers that the great Leibniz talked about in his original development of calculus. In fact, it's possible to use the hyperreal number system to develop a rigorous theory of calculus based on infinitesimals, and this is known today as non-standard analysis. So, where does all of this leave us with Pascal's wager? Well, it completely annihilates the argument. Pascal's entire calculation hinged on the assumption that a non-zero number times an infinite number is infinite. But this is not at all the case if the non-zero number is an infinitesimal. So what we're left with is an argument that collapses onto itself because it was built on unreasonable assumptions. Now, if you're a theist watching this, I'm not at all saying that you're wrong in believing in God. All I'm saying is that if you try to argue with an atheist about God, you're thinking of using Pascal's wager, you should probably think again. After all, while you may believe that the probability of God's existence is high, what's to stop an atheist from claiming that it's infinitesimal?